Hello everyone, this is Han Zhao, a PhD student from Stony Brook University, advised by Professor Xiaojun Li. This work is a collaboration between Michael Wang, Xiaolei Zhou, and Xiangshi Ren. Steering law links the movement time with ID of a task. However, it does not show how the variance of movement time changes with ID, and how the distribution of movement time changes with ID. For example, the right figure shows that the variance of movement time increases as the ID increases. In this paper, we investigate how the variance of movement time relates to ID, how the distribution relates to ID, and how to model the distribution of movement time. Our contributions are twofold. First, we propose the quadratic variance model, which reveals that the variance of movement time and ID are quadratically related. Second, we investigate how to model the distribution of movement time based on steering law and the quadratic variance model. As shown in the figure, the light blue represents the histogram of the observed data. Blue curve represents the observed PDF, and the purple curve is the predicted gamma distribution. Gamma distribution well predicts the distribution of movement time. We show how to obtain the quadratic variance model. Here, we hypothesize this quadratic variance relationship by assuming that the movement of a pointer in the steering task consists of multiple sub-movements, and each sub-movement time takes a unique time, which is a random variable t with a fixed mean mu t, and variance sigma t squared across all sub-movements. Take the constant tunnel as an example. The instantaneous speed form of steering law shows that the instantaneous speed v of the pointer is proportional to the tunnel width w. Under the aforementioned assumptions, the average travel distance of the pointer in each sub-movement is calculated, where mu t is the mean duration of each sub-movement, w is the width of the tunnel, and b is an empirically determined constant. Then, the number of sub-movements a user needs to complete the task is calculated, where a is the length of the tunnel. Therefore, the total movement time for completing the task is n times t, where t is a random variable. The variance of movement time will be n squared times sigma t squared, where sigma t squared is the variance of t, regardless of the distribution of t. Plugging the number of sub-movements and the variance of t, we can get sigma squared. Notice this part is a constant. If it is assumed that the initial sub-movement takes some extra time, we can obtain the quadratic variance model as follows. This equation is referred to as the quadratic variance model, and it shows that the variance of movement time is quadratically related to ID. For non-constant tunnels, the explanation is similar. Besides the quadratic variance model, we also introduce 5 other candidates to model the variance. They are constant, linear, and quadratic form with different complexity levels. Model 4 is shown as the quadratic variance model. Model 1 and Model 3 are introduced to investigate whether quadratic term would help to improve the fitting accuracy, while Model 2, 5, and 6 are compared with Model 4 to see whether a candidate with higher or lower complexity would benefit model fitness. Combining the variance models with steering law, we can predict the distribution of movement time. We introduce 6 types of distributions, which are Gaussian, truncated Gaussian, log normal, gamma extreme value, and exponential modified Gaussian distributions. Among them, log normal, gamma, extreme value, and X-Gaussian are positively skewed distributions, while Gaussian and truncated Gaussian are symmetric or near-symmetric distributions. Take the gamma distribution with the quadratic variance model as an example. We use the steering law to predict the mean, and the quadratic variance model to predict the variance of movement time. Then we express the model parameters in terms of the mean and variance. For other types of distribution models, we follow the same method. For X-Gaussian distribution, it naturally applies a quadratic relationship between the variance and ID. Next, we evaluate the variance model using maximum likelihood estimation and distribution model using Bayesian modeling on Zhou and Ren's and our newly collected dataset. Zhou and Ren's steering dataset includes 10 participants and 9 conditions. Our result shows that the quadratic variance models has the highest or second highest R-squared value and the lowest leave-one BW condition on cross-validation, root mean square error, AIC and WAIC, and it outperforms other variance models. The distribution modeling results suggest that the positively skewed distributions like log normal, gamma, extreme value, and X-Gaussian distribution outperform Gaussian and truncated Gaussian distributions. Gamma distribution performs the best among all the distribution models. The posterior predict checks shows that the gamma distribution in purple resembles the observed PDF and perform better than other distributions. Similar to the evaluation of Zhou and Ren's dataset, we carry out an experiment on our new dataset. We recruited 12 participants with 12 conditions. Our results show that the quadratic variance model performed better than other variance models. The distribution modeling results shows that log normal, gamma, extreme value, and X-Gaussian distribution outperform Gaussian and truncated Gaussian distributions. Gamma distribution performs the best. The posterior predict checks also shows that the gamma distribution in purple looks very similar to the observed PDF and outperform other distribution models. In this research, we propose a quadratic variance model which reveals that the variance of movement time and ID are quadratically related. Also, our results suggest that the positively skewed distributions such as log normal, gamma, extreme value, and X-Gaussian perform better than Gaussian and truncated Gaussian distributions. Gamma distribution performs slightly better than other distributions in most cases. Overall, our research advanced the movement time prediction from a mean estimate to the variance and distribution estimates for steering tasks.